we have studied about heat engine. In heat engine, the heat is taken from one source. We call it reservoir, which is at a higher temperature, and it is allowed to flow out to the sink. Heat flows from higher temperature reservoir to low temperature sink, and in between work is done by an agent. Today we will study the practical aspect of it, how there are variations of pressure, volume and temperature in working of an heat engine. So in the heat engine, basic ingredient or the elements remain same. There will be one source which is at a higher temperature, from which we can take the heat energy. Then there is a sink where can reject the heat, and there has to be one working agent. For this purpose, Carnot described a working pattern, and that working pattern is known as Carnot cycle. Carnot cycle is a cyclic process. It starts with a particular parameter, that is a working agent. Here we take this working agent as an ideal gas, because it is a theoretical engine. We can always take ideal things. So we take an ideal gas to understand it. This ideal gas has a certain pressure, volume and temperature, and this goes on changing. It can take the heat from reservoir, it can reject the heat to sink. It has a capacity to extend so that it can do the work. We can always compress it to reduce the volume. This is what we can do with the gas, or we can do on the gas. Now, once again, we come to the elements. In this we will calculate, Carnot cycle, we will calculate how much work is done by an engine related to its parameter, that is related to change of its volume and changes of its temperature. This is a cyclic process. That means the pressure, volume and temperature, they keep on changing, but after certain changes they come back to their original position, original values. So this is a cyclic process. In this cyclic process, we have gone through that there may be two types of processes related to heat and temperature, and one is isothermal, other is adiabatic. So in this, when heat is absorbed, work is done. We will allow that this work is done by isothermal method as well as adiabatic method. Let both the methods work. Again, when we compress, then the heat is absorbed, the heat evolves, and it may be a method of isothermal, it may be a method of adiabatic. So all these things are shown, and this process is shown in this Carnot cycle. Okay, so in Carnot cycle, our elements are one which gives the heat, reservoir, and one which absorbs the heat, that is sink, and there is one working substance, ideal gas. To get the work done by the ideal gas, we have to use a device, and that device is a cylinder and a piston. Cylinder and piston, I will describe you. It's a device in which whenever there is an expansion, we convert the expansion work to the mechanical work. It's a device in which when we compress it, then heat is formed, and that heat can be taken out, or it can increase the temperature. Okay, so let's first see the elements of heat engine. The first thing is that there is one source of high temperature which is known as reservoir. The specialty of reservoir is whichever amount you take from the reservoir, its temperature will not become less. Its temperature will not reduce. It may appear contrary to our principles that whenever heat is taken out, the temperature has to reduce. But in this particular case, we think that our reservoir is such a large reservoir that whatever amount of heat is taken, and we are taking a very small amount of heat compared to that. Or in a particular process, whenever we take out heat, if the temperature is going to decrease, something from the source comes up and makes it up. इसे इस तरह से समझिए कि समुद्र में से हम पानी ले रहे हैं, उसके पानी का लेवल कम नहीं होता. The same thing from the sun, we are taking the heat, सन का टेम्परेचर कम नहीं होता. प्रैक्टिकली देखिए, हम एक मोटरसाइकिल चला रहे हैं, मोटरसाइकिल के इंजन के अंदर जहां पिस्टन है उसके ऊपर पेट्रोल जलता है. वो पेट्रोल वहां जलता है, उसका एक टेम्परेचर होता है T1. पेट्रोल हमने जलाया, उससे पावर ली, धुआं निकल गया, स्मोक इज आउट, तो उसका टेम्परेचर कम होना शुरू हो जाता है. नेक्स्ट सप्लाई ऑफ पेट्रोल आती है, वो जलता है और फिर से टेम्परेचर T1 हो जाता है. फिर पिस्टन चलता है, गाड़ी आगे चलती है, धुआं निकल जाता है, वो टेम्परेचर T1 कम होने लगता है, फिर से पेट्रोल आता है, जलता है, उसका टेम्परेचर T1 मेंटेन हो जाता है. दिस इज रिजर्वायर. सन इज ए रिजर्वायर, ocean is a reservoir. This our petrol engine where petrol is burning is a reservoir till we are supplying the mixture which can burn. So in this way we can have reservoirs. Again, sink. Sink is something in which we can reject heat. We can give heat to the sink without change in temperature. If we want, मेरे पास एक गरम चाय का कप आता है और मुझे उसे ठंडा करना है, तो मैं उसे यहाँ रख देता हूँ. एटमॉस्फेयर की हवा से, एयर से उसको टच होकर उसका टेम्परेचर डाउन हो जाता है. डू आई एक्सपेक्ट कि हवा का टेम्परेचर ज़्यादा हो जाएगा? नहीं होगा, क्योंकि कप की कैपेसिटी बहुत कम है और एयर की क्वांटिटी बहुत ज़्यादा है. दिस इज सिंक. तो सिंक ऐसे ही होंगे. अगेन, ocean water is a sink. It's a very large sink. Our atmosphere is a sink. And atmosphere is a sink. The same phenomena, the same fact we use in our motorcycle, in our cars. साइलेंसर से जला हुआ धुआं निकलता है और एटमॉस्फेयर में चला जाता है. That quantity is very small compared to atmosphere. तो एटमॉस्फेयर का टेम्परेचर इंक्रीज नहीं होता. That is what we generally presume. तो ये एटमॉस्फेयर हमारे लिए क्या काम करता है? ये एक सिंक का काम करता है, जिसमें आप जितनी भी हीट दे दीजिए, the temperature will not change. Okay, so these are the sinks. And now see, I will make a block diagram how we are going to make the different elements appear. This is a reservoir. It has a high temperature T1. This surface of the reservoir is a conducting surface. From here heat can be transferred very easily. Anything we place on it, this can give the heat to that body, or that body can give the heat to it. Then we have a sink. This is a representation of a sink which is at a lower temperature T2. Okay. Again, let us assume that this surface is a conducting surface from where heat can transfer. Then for our convenience, we make one insulation pad here. Okay, this is all insulated. Anything placed on it will get sealed and the heat cannot be transferred. Then we have working substance. Working substance will be contained in a cylinder. This is a cylinder. The specialty of the cylinder is that the walls are insulated. Walls are adiabatic, walls are insulated. We will make a diagram. This one side is conducting. Then there is a piston which can move freely in it. This is a piston which can move freely, and this is connected with a rod here. So this is just a representation that how it mechanically works, and this piston can move up and down. And here we have the ideal gas, which is our working substance. Working substance, and this working substance is ideal gas. Okay, then we have our mechanical engines. Here we have engine, or here. So when it moves up, the wheel will rotate. This is a crank system. Okay, it is not a part of the heat engine. It is just to show that by the expansion we can get the work done. Okay, so piston, this is cylinder. This cylinder is insulated walls. But this one surface is conducting surface, rest all the surfaces are insulated. इसमें से heat नहीं जा सकती, सिर्फ इसमें से heat जा सकती है. It is capable of moving. Okay. So this is our working substance, and this cylinder is such that for our process we will keep on placing it here, here or here, anywhere we want we can place it. Okay. Now with these three we start working in different steps. What we have to do, we have to absorb the heat from reservoir. So this process will be done in 4 steps. We have given names to the 4 steps according to whatever is done in that process. So it is a cyclic process. It keeps on continuing. We can start from any one place. So we will start from a step where this working substance is placed on reservoir. It has got particular parameters, and those parameters are, I will make the diagram here. Okay, this is cylinder. In the cylinder there is piston. Here is the working substance, gas. Okay, it is placed here. At this particular juncture, it has pressure P1, it has volume V1, it has temperature which is T1. The temperature is T1, it has volume V1, it has got pressure P1 at a particular instant. Think. Okay, now the process which takes place. We will take 4 steps in the process, and for every process we will write certain steps so that we remember clearly and we don't leave out any detail. The first thing is name of the process. The name of the first process is isothermal expansion. Where does it take place? That we will write again. Cylinder has ideal gas as working substance. It has pressure P1, volume V1, and temperature T1. These are the parameters it's having. Then after that, now we will describe in the second step what is the action being taken. So this is first thing where the step is taking place. So it is taking place on reservoir. Cylinder has ideal gas as working substance. It has pressure this. It is kept on reservoir. This. Then in the second, what is the action? What is the process? The working substance, or I will write it gas, absorb heat. The gas absorbs heat. And what happens after absorbing heat? Its volume expands. What happens to temperature? Temperature remain constant. What happens to pressure? When volume expands, the pressure reduces, it decreases. Pressure decrease from P1 to P2. Volume increase, we can note it V1 to V2. Volume increase, yes, write down. Volume increase V1 to V2. Pressure decrease P1 to P2, and the temperature remain constant, that is T1. Why? We have a thing that there are two type of processes in compression. One is isothermal and one is adiabatic. This is isothermal part of that. Because it is isothermal, there will be no change in temperature and it will remain T1. So the pressure decrease from P1 to P2, temperature remains same. This is what happens. So this explains where it is. This explains the happening, what is happening. Third, we will mention the status of work or the status of energy. So in this process, whenever there is expansion of the gas, the piston will rise up and the work is done. Who is doing the work? The answer is gas is doing the work. The gas is using heat energy taken from the reservoir and it is doing the work. So, heat taken Q1, heat taken is Q1 from reservoir. Work done work done. Let's call this work done in step number 1, W1. This is an isothermal expansion, so there is no change in temperature, there is a change in volume, and we have already derived an expression for work. When the volume changes from V1 to V2 at temperature T1, then the work done is mu R T1 log V1 upon V2. This is the amount of work done. This we have done in the previous class. So this is work done mathematically. Okay. Then after this, these are the expressions, and we will make a indicator diagram. The indicator diagram will show the changes in pressure and volume, and it will also show how much work has been done. So let's make an indicator diagram for the process number 1, and here is that indicator diagram. This is volume, this is pressure. The initial parameters are pressure P1, pressure P1, volume V1. The volume is increasing here, the pressure is increasing here to the top. This pressure we suppose is a high pressure. Pressure 1 is a high pressure, and the gas is already in compressed state, which will expand after taking the heat. शुरू में जब हमने लाके रखा था तो वॉल्यूम कम था, प्रेशर हाई था. This was the state. Volume कम, pressure high, and this was pressure was P1 and volume was V1. When there is expansion taking place, the volume goes on increasing. Volume increase हो जाएगा, pressure decrease हो जाएगा, and ये यहाँ आ जाएगा. जिससे देखिए वॉल्यूम इंक्रीज, प्रेशर डिक्रीज. और ये जो प्रोसेस होती है, दिस इज आइसोथर्मल प्रोसेस, एंड वी हैव ऑलरेडी डन दैट. दिस इज हाउ द आइसोथर्मल प्रोसेस अपीयर्स. दिस इज एट टेम्परेचर T1. This is at temperature T1, but the pressure and volume has changed, so this we will write as P2, V2, and the temperature is same T1. Let us say this point is A, this point is B. Okay, and the direction of process is expansion, so we will put an arrow here. This arrow indicates that it is an expansion, and the name of this process is isothermal expansion. You can write it here, it will be a bit crowded, but we can always write isothermal expansion. Okay, so this is the one step which is done. How much work is done in this? The work done in isothermal expansion or in any PV indicator diagram is given by the area under the graph. So here, this area gives the work done during this expansion, and we can give it a name. This is work done. So in this process, how much is work done? Work done. Area A, B, A, B, G, E. A, B, G, E. A, B, G, E. This is represented by, work done is represented by area A, B, G, E in indicator diagram. Okay. So this is detail of our one step of the process in Carnot cycle. And what is this process? Name of the process? Isothermal expansion. Isothermal expansion. Now, when this isothermal expansion takes place, there are some expansions which are adiabatic also. We have to take care of that also. We allow the gas to expand and expand and expand, and its temperature will become down. That process in which temperature changes but heat contents do not change is adiabatic process. So the second process now is adiabatic expansion. So both type of expansions will be there. One is isothermal, one is adiabatic. To show that there is an adiabatic expansion, in the second step, we take our working substance to the insulation pad. So this was step number 1. As step number 2, we are keeping this cylinder on adiabatic pad, and here is the piston. Okay, now you see this was insulated from 3 sides. This was conducting. Here this is conducting, but the pad is insulated. If this pad is insulated, then this path of heat transfer is also closed, and this becomes a completely adiabatic enclosure. The heat cannot come out, the heat cannot leave it. If heat cannot leave it, then if there are certain changes, the temperature will change, but the heat will not change. Now, in this, what do? We allow it to expand more. Here its expansion is taking. Here also we allow it to expand whatever expansion it wants to, and we allow it to expand so much that its temperature become down. It has come here with pressure P2, volume V2 and temperature T1. Then here is in the pressure 2, there is expansion, adiabatic expansion. After expansion, this volume will change to V3. The pressure will again decrease to P3. But heat is not allowed to enter, therefore the temperature will change. What happens when volume expands? This we have done in our thermodynamics equation, the first law, that whenever there is an expansion of volume, the temperature will decrease. So there is a change in temperature, and this temperature decreased to T2. So after this expansion, which adiabatic expansion, this volume increases and the temperature becomes down. This is what happens here. Now this process what I have told you, now we will write it. That is process number 2. The name of this process is adiabatic expansion. Where does it take place? Cylinder is kept on insulation pad. Surface become adiabatic. Heat cannot leave or heat cannot come. Acha. Then process. Gas is allowed to expand further. Gas is allowed to expand further from V2 to V3. From V2 to V3. Okay. Then pressure decrease to P3. Because it is an adiabatic process, the temperature will also change and temperature decrease to T2. This is about volume, pressure and temperature in step number 2, adiabatic expansion. Now we will show it. Now, third step is how much is the work done. Work done. This is an adiabatic and we have got the expression of adiabatic. The work done W2 is equal to R, the change in temperature is T2 minus T1. This is the work done for 1 mole, okay, or for mu moles. This is work done in adiabatic process, okay. How do we show it in this? There is an increase in the volume, there is a reduction in the pressure, pressure decrease, volume increase, and we get another point here, and this is this. Now, this point, this is the direction, this direction shows that it is an expansion, and this is adiabatic expansion. Let us say this point is C. The parameters here are P3, V3. The temperature has changed to T2. Okay, and this is expansion. How much work is done in this? The work done is the area under the graph. So, this is area under the graph. So we will give it a name. This is represented by area BCHG. आप सबको याद होगा, वर्क डन हैज ए फॉर्मूला P into V, pressure into volume. This is pressure, this is volume, और एरिया का फॉर्मूला क्या होता है? Length into width, pressure into volume. So area is pressure into volume, but pressure into volume is the work done. So area represents the work done. Therefore, represented by area BCHG, and what is this? Gas is doing the work or we are doing the work on the gas? Answer is the gas is expanding. So work is done by the gas. So work done by gas. This is important. By. So work done by the gas is this much. This is our explanation of the second process. Now, what has happened so far? So far, it has expanded fully. Here, it has expanded fully. Now, it cannot expand anymore. गैस जितना काम कर सकती थी, उसने कर दिया. अब गैस ने पूरा काम कर दिया. हमको और चाहिए काम. अगर हमको और काम चाहिए, तो हमको उस प्रोसेस को दोबारा करना है. अगर हमको दोबारा करना है, तो हमको इसको फिर से यहाँ पहुँचाना पड़ेगा. पर इसको अगर हम यहाँ दोबारा पहुँचाना चाहते हैं, तो इसका टेम्परेचर T1 होना चाहिए, इसका वॉल्यूम V1 होना चाहिए और इसका प्रेशर P1 होना चाहिए. तो उसको करने के लिए हम एक और प्रोसेस करते हैं, और वो प्रोसेस है हमारी, दैट इज स्टेप नंबर 3. दिस वी ब्रिंग टू द सिंक. इसके अंदर अब तक क्या हो रहा है? इसने कुछ इसको हीट दी हुई है. ये हीट अभी इसके पास है. और ये एक्सपेंड होके हमारा काम कर चुका है। तो उस हीट को अगर हमने फ्लो कराना है तो इट इज नेसेसरी दैट heat goes to the sink so that the flow of heat is there. Now heat goes to the sink. उसके लिए हम इस सिलेंडर को उठाकर यहाँ रख देते हैं। This. Now these three sides are adiabatic, insulated, and this one side is conducting. This one was conducting, it was giving heat. This one is conducting, heat can come out. So this is our step number 3. And what are we doing here? The answer is we are compressing it. इसको हम नीचे ले जा रहे हैं। यहाँ पर क्या हो रहा था? ऊपर जा रहा था। यहाँ पर भी क्या हो रहा था? ऊपर जा रहा था। The work is done by the gas, it goes up. Work is done by the gas, expansion, it goes up. It has gone to the maximum. इससे और ऊपर ये नहीं जा सकता। I will change it. Let's make it this way. अब इसके ऊपर वो और नहीं जा सकता, जितना वर्क कर सकता था उसने कर लिया। टू ब्रिंग इट बैक वी पुट इट हियर एंड कंप्रेस इट। जब हम इसको कंप्रेस करते हैं, थोड़ा टेम्परेचर पे ध्यान दीजिए। दिस टेम्परेचर वाज T2, लोअर टेम्परेचर। व्हेन वी प्रेस इट दिस विल गेट हीटेड अप, द गैस विल गेट हीटेड अप, बट द हीट इज इमीडिएटली टेकन बाय द सिंक and the temperature is not allowed to increase. So temperature will remain T2. So whatever compression we are doing, the compression is there, volume is decreasing, pressure is increasing, but temperature does not change. So what we are doing is isothermal compression. Okay. Now we have pressed it, compressed it. After compression, the volume has decreased to V4. The pressure, when we compress it, the pressure will increase and this pressure will be now P4. This is an isothermal process. The heat is going out or coming in, but the temperature is not allowed to change. So the temperature remains T2. This is our step number 3 done. Now we will write it. The name of the process is isothermal compression. Isothermal compression. Where it is taking place. So the gas is kept on sink and it is compressed. Pressure increase P3 to P4, volume decrease V3 to V4. What happens to temperature? Temperature increase, no, temperature remains same because it is isothermal. Temperature remains same T2. So this is where we do it. This is what happens in this process. So, who is doing the work? The work is done on the gas. The work is done on the gas, and how much is this work? We can write it this work. Now this is an isothermal process and there is a compressor. The volume has changed from V3 to V4, so the work done will be W3, and this work is equal to mu R at temperature T2, and the volume has changed V3 to V4. So this is the work done in this process. Okay. Now can we show it by the indicator diagram? Yes. Given by area, यहाँ पर देखिए किस एरिया में हमको मिलेगा. The answer is the volume has decreased, the pressure has increased. Volume decrease, pressure increase. So it will go somewhere here. This is and this process, okay, this should never come down because the volume goes on, pressure goes on increasing, it goes up and it goes in this direction. So this is the direction. This direction shows compression. This arrow shows expansion, this arrow shows compression, and this is isothermal compression. And we have reached the new element parameters, and this parameter is the pressure has increased to P4, here it is P4, volume is V4, the temperature, isothermal process, the temperature remain T2, and let this point be D. How much work is done on the gas? Answer is the area below the graph. Where is area below the graph? I will make it here. This is area below the graph. What is that area? Start from here and here. So this is the area. This area shows the work done on the gas by this process number 3, isothermal compression. And now I can write it here. Given by area DCHF, given by area DCHF HFD again. It is given by this area. Here there is a change in volume V3 to V4. So this is mathematical expression for the work done on the gas. This is graphical expansion DCHFD. Graphically this much is the work done in the process number 3. So now we have done the process number 3 and the gas has been compressed. The temperature is T2. Process number 3. Now after that we place this working substance on the pad again, on the pad. This from 1 to 2, 2 to 3. Now what we do, we bring it back to the pad this way, and that will be process number 4. In the 4, what we do, we put it here and compress it suddenly. Compress it more so that there are adiabatic compressions. So our 4th process is adiabatic compression. When we press it more and this is insulated from all the sides, the heat cannot go out. If the heat cannot go out, then what will happen to the temperature? The temperature will increase. If the temperature increase, there are changes in the temperature, and we press it so much that the temperature goes on increasing, and we bring it to the temperature T1. The pressure is increased, the volume decreased, the temperature become T1, the pressure is increased so much that it become pressure P1, the volume become V1, and the temperature become again T1, and by this compression you see the temperature is increasing, we increase it up to T1. The volume is decreasing and we decrease it up to the value of V1, and the pressure we compress it to the pressure P1. So this is done at this point. So on this point again we reach P1, V1, T1. When we are compressing the gas, we are doing work on the gas. So working on the gas, there are two steps. One, isothermal. When we are compressing it, the temperature remain constant, and the other is adiabatic compression. Let there be change in temperature, but we do the compression very fast so that its temperature again rise to T1, and we reach to the point number 1 again. Here we compress it. यहाँ से इतना compression करेंगे that volume will decrease this much, the pressure increase this much. This is pressure P1, this is pressure P4. तो हमने उसको इतना compress किया suddenly कि P4 से बढ़ के pressure P1 हो गया, P1, और volume compress होके V1 हो गया. इस process में this is the point. What is the direction of process? This. What does this mean? Expansion or compression? Yes, it is compression. So this arrow shows compression, this arrow shows compression, this is isothermal compression, this is adiabatic compression. And we compress it so much that it will reach the P1, V1 and T1 parameters again. Okay, so we are again back at the end of the 4 cycles, reach here. And what is this 4th step? This 4th step we have allowed temperature to change, so this is adiabatic compression, and this we will write adiabatic compression. What will be the area in this? Area represent what? Area, this area under the graph, this area. This represents the work done on the gas. This was work done by the gas, area below it. This is representing work done on the gas. Okay, if we make it like this, I will put it this way. Yes, this is work done by the gas. और ये भी work done by the gas. Out of this we have to do work done on the gas, and this is work done on the gas, this is work done on the gas. If this was the total work done by the gas, this is the work done on the gas, then what is this? This is our saving. The work done by the gas is more and work done on the gas is less. जैसे इसका एग्जाम्पल देखिए, हमने कार में या मोटरसाइकिल के पिस्टन के ऊपर पेट्रोल को बर्न किया. पेट्रोल को बर्न करने से गैस एक्सपेंड हुई, दोनों तरह के एक्सपेंशन हुए, एंड द वर्क डन इज आइसोथर्मल एज वेल एज adiabatic. How much work is done? We have done the work here, this much. Let us suppose the work done is 100 joule. द वर्क डन बाय द गैस इज, सपोज इट इज 100 जूल। उस वर्क ने क्या किया? ये वर्क हमारे दो काम हम उससे करवा लेते हैं। एक तो ये है कि यहां पर देखिए, इसको पिस्टन को हमने ये जो पिस्टन ऐसे ऊपर जाता है, उस समय हमने इसको ये एक क्रैंक के साथ जोड़ा हुआ है, ये एक व्हील के साथ जोड़ा हुआ है। दिस इज ए फ्लाई व्हील विच हैज लॉट ऑफ मोमेंट ऑफ इनर्शिया। ये जैसे ऊपर जाती है कितना वर्क करती है? 100 जूल। इस 100 जूल में से 40 जूल इसने खर्च कर दिया इसको घुमाने में, बाकी 60 जूल इसी के साथ हमने अपना मोटरसाइकिल का व्हील लगाया हुआ है, तो ये भी घूमता है और व्हील भी घूमता है। 40 जूल इसको घुमाने में खर्च होता है और 60 जूल उस व्हील को घुमाने में खर्च होता है, जो हमारी मोटरसाइकिल का व्हील है, चक्का है, और मोटरसाइकिल ऐसे आगे चली गई। तो मोटरसाइकिल में मूवमेंट स्टार्ट हो गया, मोशन स्टार्ट हो गया। किससे? 60 जूल से। 40 जूल कहां गया? 40 जूल से तो खाली एक फ्लाई व्हील हवा में ऐसे घूम रही है। ओके, मोटरसाइकिल आगे गई, इसका 100 जूल खर्च हो गया और ये पिस्टन ऊपर पहुंच गया। अब जब ये पिस्टन ऊपर पहुंच जाता है, हमने इसको यहां पर ऊपर पहुंच गया, इसको कंप्रेस करना है। अब कंप्रेस करने के लिए कौन काम करता है? तो आंसर है फ्लाई व्हील काम करती है। उस फ्लाई व्हील के पास कितनी एनर्जी है? 40 जूल। ड्यू टू मोमेंट ऑफ इनर्शिया इट कीप्स ऑन मूविंग, वो रुकती नहीं है। तो ये पिस्टन जब ऊपर पहुंच भी जाता है तो ये अपने मोशन के कारण इस पिस्टन को फिर से नीचे दबा देती है और अपनी वो 40 जूल वाली एनर्जी यूज करती है और इसको कंप्रेस कर देती है। और जब भी इसको कंप्रेस करती है, व्हाट वी से, द वर्क इज डन ऑन द गैस। तो वर्क इज डन ऑन द गैस इस केस में किसने किया? फ्लाई व्हील ने किया। ओके, फ्लाई व्हील को एनर्जी कहां से मिली? शुरू में जब गैस एक्सपेंड हुई थी उसने 100 जूल एनर्जी हमको दी थी, उसमें से 40 जूल हमने रख ली थी। किस काम के लिए? कि उसको पिस्टन को हम दोबारा दबाएंगे। उसी की एनर्जी से हम पिस्टन को दोबारा दबाते हैं। अगर वो नहीं होता तो हम किक मारते, किक मार के पिस्टन को दबाते। किक नहीं है, सेल्फ स्टार्टर लगा के दबाते, पर कंप्रेशन, उसको हमको कंप्रेशन देना है, तब हम जाकर P1 V1 T1 तक पहुंचेंगे। तो ये P1 V1 T1 तक पहुंचाने का जो काम है, ये हम किक से करते हैं, सेल्फ से करते हैं एक बार, और जब गैस वर्क डन करके हमको देती है तो उसमें से हम थोड़ी सी एनर्जी से फ्लाई व्हील घुमा लेते हैं। वो फ्लाई व्हील उसको बार बार P1 V1 T1 तक पहुंचा देता है कंप्रेस करके। दिस इज व्हाट इज डन एंड दिस इज वर्क डन ऑन द गैस। ये हमने किससे कराया? गैस के वर्क से ही कराया। देखो, गैस ने हमको ये पूरा वर्क दिया था, उसमें से इतना वर्क हमने किसमें यूज कर लिया? इसको दोबारा यहां पहुंचाने में। उसमें ये वाली जो वर्क डन है, ये वर्क डन हमारी सेविंग हो गई। ये हमने कहां यूज किया? कार को आगे बढ़ाने में, मोटरसाइकिल को आगे बढ़ाने में। दिस इज अवर सेविंग इन वन साइकिल। तो अब हम इसमें स्टेप नंबर 4 को लिख लेते हैं। एंड व्हाट इज दैट स्टेप नंबर 4? स्टेप नंबर 4 इज एडियाबैटिक कंप्रेशन। ओके, तो ये एडियाबैटिक कंप्रेशन में कहां पर होता है एडियाबैटिक कंप्रेशन? एडियाबैटिक कंप्रेशन इज अगेन डन ऑन द पैड। व्हाट डज इट डू? P4 V4 T4 जो हो चुका है, यहां पर ये जो कंप्रेशन हुआ था, इस कंप्रेशन से हमको रिजल्ट क्या मिले थे? P4 V4 एंड T2। ये P4 V4 T2 को कंप्रेस करते हैं एडियाबैटिकली और कहां पहुंचा देते हैं? P1 V1 T1, और ये यहां चला गया। फिर से दूसरा साइकिल स्टार्ट होगा। सो दिस इज P1 V1, यहां पर P2 V2 आया, यहां पे P3 V3 आया, फिर इसको कंप्रेस किया, P4 V4 हो गया, P4 V4 को और कंप्रेस किया, P1 V1 T1 हो गया। दिस वन साइकिल इज कंप्लीट। इसने हमको यहां पर 2 बार एक्सपेंशन हुआ, इसने हमको एनर्जी दी। उस एनर्जी का एक पार्ट हमने वर्क इज डन ऑन द गैस, यहाँ एक कंप्रेशन, यहाँ दूसरा कंप्रेशन, अगेन इट रीचेज देयर, पर इस प्रोसेस में वर्क डन बाय द गैस इज ऑलवेज लार्जर देन द वर्क डन ऑन द गैस। ऐसा हम फ्यूल यूज करेंगे कि वर्क डन ऑन द गैस विल ऑलवेज बी मोर देन वर्क डन on the gas. Work done by the gas will be more than work done on the gas, and every cycle we are saving this work. So इस ग्राफ में, इंडिकेटर ग्राफ में एक चीज याद रखिए, व्हाट इज द रिप्रेजेंटेशन ऑफ एरिया इनसाइड कार्नोट साइकिल। ये कार्नोट साइकिल बना, यहां से स्टार्ट हुआ और वहीं पर वापस पहुंच गया। दिस इज ए साइक्लिक प्रोसेस, एंड व्हाट इज दिस साइकिल? कार्नोट साइकिल। तो कार्नोट साइकिल के अंदर का एरिया क्या रिप्रेजेंट करता है? दैट इज वर्क डन बाय गैस पर साइकिल। ओके, तो पहले हम इसकी फोर्थ प्रोसेस लिख लेते हैं, फिर और बाकी डिस्कस करेंगे। फोर्थ प्रोसेस में हमने क्या लेना है? एडियाबैटिक प्रोसेस। सो वी विल गो फॉर राइटिंग हियर फोर्थ प्रोसेस। Okay, so this is adiabatic compression. How much work is done? This is work done on the gas. Represented by area, आप लोग इसको लिख चुके हैं. This is DC HF. Represented by area DCHFD. Okay, this is okay. After that, what happens? Parameters are P1, V1, T1, and we can start the cycle once again. So, how much is the net work done in this total 4 steps? Net work done. वर्क डन बाय द गैस कब हुआ था, प्रोसेस 1 और प्रोसेस 2 में। तो उन दोनों की रीडिंग हम यहाँ पर लिख लेते हैं। प्रोसेस 1 और प्रोसेस 2 में क्या वर्क हुआ था उससे माइनस कर देंगे प्रोसेस 3 और प्रोसेस 4 का वर्क डन। सो दिस विल बी W1 प्लस W2 माइनस W3 माइनस W4, ये हमने करने हैं। सो वी विल राइट इट फ्रॉम द एक्सप्रेशंस व्हाट वी हैव रिटन। सो दीज आर द एक्सप्रेशंस, वर्क डन ऑन द गैस, isothermal adiabatic, this is isothermal adiabatic. In this you will find that V1, V2, V3, V4 are different, but T1 minus T2 temperature difference and here is temperature difference, both are same. In adiabatic process, when we are doing work on the gas, the quantity of work is this much. When we are doing work on the gas, this is the quantity and this is the quantity of work done by the gas, and these two quantities are same. Okay, so don't think about T1 minus T2 or T2 minus T1, does not matter. What we understand, work is done on the gas, work is done by the gas, the quantity is temperature difference, the quantity is temperature difference, and both temperature differences are same, mu and r are same. So work done by the gas is equal to work done on the gas in adiabatic only. So these two are equal to each other. One's nature is by the gas, it has nature on the gas, so when we add it up they cancel each other and they cancel each other. So what do we get the net work done? Net work is equal to here mu r T1 log V2 upon V1 minus mu r T1 log V2 upon V1, and this is V3 upon V4. This is the net work done. And what are these processes? So this is isothermal expansion, isothermal compression. So work done depends upon which process, isothermal process or adiabatic process? Yes, the answer is isothermal process. Work is done by isothermal process only. This is net work done. It is represented by which area? Represented by area CD, what you see in this graph. This is the net work done by this area, net work done by this one cycle of Carnot's engine. So this is the work done. अब इसमें next हम निकाल सकते हैं what is efficiency of the Carnot cycle. Efficiency निकालने के लिए हमारे पास क्या फॉर्मूला है? Efficiency of Carnot cycle, eta is equal to work done heat given, net work done, and how much heat we had given, Q1. Okay, so this work done is how much? This work done we can write, we know it here, this is the work done. Okay, now this again we can simplify. Q1 is the work done in the first step in isothermal process. The heat was taken. Heat was taken in the isothermal process. So that was the heat taken Q1. So this now we can write as, in place of Q1, we can write this heat taken by the gas, mu RT1 V2 upon V1. Mu RT2 और कितनी हीट ली गई थी उससे, म्यू RT1 log V2 ये शुरू में हमने हीट ली थी. सो दिस इज एक्सप्रेशन फॉर ईटा. नाउ वी कैन सिंप्लीफाई इट. म्यू आर इज कैंसल्ड. This expression for efficiency reduced to efficiency, इसको हमने इससे डिवाइड किया, ये कितना आ गया 1 माइनस इसको इससे डिवाइड किया T2 अपॉन T1 और ये दोनों इक्वल होते हैं, ये दोनों इक्वल होते हैं और कैंसल आउट हो गए. तो ये कैंसल आउट हो गया. ये T2 अपॉन T1 वो हमने यहां पर लिख लिया T2 अपॉन T1. सो दिस इज आवर एफिशिएंसी फॉर्मूला. ठीक है, आराम से सोचिए. वर्क डन Q2 माइनस Q1 ये हमने ऊपर निकाला, डिवाइडेड बाय Q1 क्या है, हीट टेकन इन दी आइसोथर्मल प्रोसेस, द वेरी फर्स्ट प्रोसेस. दिस इज द हीट टेकन Q1. डिवाइड करना है, म्यू आर कॉमन निकला, कैंसल हो गया. V1 अपॉन V2 इज इक्वल टू V3 अपॉन V4 होता है. दैट वी कैन प्रूव बाय गैस लॉज. इसलिए ये दोनों कैंसल हो जाएंगे. बचेगा क्या, यहां पर बचेगा दिस. इसको इससे डिवाइड किया, T1 अपॉन T1 1, T2 अपॉन T1 T2 अपॉन T1. दिस इज एफिशिएंसी ऑफ ए कार्नोट साइकिल. Now, can the efficiency of Carnot cycle can be 100%? No, because T2 upon T1 can never be 0. T2 कभी भी 0 नहीं हो सकता, T1 कभी भी infinity नहीं हो सकता. So this will have certain value and 1 minus something is less than 1. So efficiency is always less than 1. As always less than 1. ये एक चीज होगी. ओके, दूसरा, अगर हम कोई भी प्रैक्टिकली इंजन बनाते हैं, एनी इंजन, देखिए कार्नोट साइकिल किसी एक इंजन का नाम नहीं है, ये एक जनरल प्रिंसिपल का नाम है, एक प्रोसेस का नाम है. और इस दुनिया में हर चीज जो हीट से कन्वर्ट कर रही है मैकेनिकल वर्क, हीट टू मैकेनिकल एनर्जी, जो भी कन्वर्शन हो रहे हैं सब इसी प्रोसेस पे काम करते हैं. भले वो कार का इंजन है, मोटरसाइकिल का इंजन है, एरोप्लेन का इंजन है, या हमारी बॉडी है। हम कुछ खाते हैं, हीट बनती है, मैकेनिकल वर्क हम करते हैं, दैट इज ए कन्वर्शन। भले अर्थ हो, अर्थ को सन से हीट मिलती है, वो वर्क करती है, उसकी एफिशिएंसी है। अर्थ मूव करती है, घूमती है, अर्थ के ऊपर इतनी प्रोसेस हो रही हैं, ये सब वर्क डन बाय द अर्थ है। फिर वो हीट को रिजेक्ट कर देती, रात को, दिन को एब्जॉर्ब करती, रात को रिजेक्ट कर देती है और बाकी वर्क करती है। तो इस तरह से दुनिया की हर चीज जो हीट ले रही है और वर्क कर रही है, दैट इज ए हीट इंजन, और हर एक में ये प्रोसेस एप्लीकेबल होती है, कार्नोट साइकिल। हर एक में आपको एक सोर्स ऑफ हीट मिलेगा, हर में एक सिंक मिलेगी जहां हीट रिजेक्शन हो रहा है, और एक ऐसा मटेरियल मिलेगा जो सोर्स से हीट उठाता है, सिंक में जाके रिजेक्ट करता है और बीच में वर्क कर देता है। एवरीवेयर इट इज लाइक दिस। भले वो हमारे ब्लड हैं, मसल्स हैं जो ये काम करते हैं, भले दूसरे सिस्टम में, इंजन में पेट्रोल की गैस ये काम करती है। इस तरह से हर जगह पर हमको कोई ना कोई चीज मिल जाती है। और आइडियल चीज क्या है? आइडियल गैस, जिससे हम इसको एक्सप्लेन करते हैं। तो ये जितने इंजन होते हैं, इसके लिए ना इनकी एफिशिएंसी कितनी होगी? तो आंसर है एफिशिएंसी जो भी होगी, लेकिन इससे ज्यादा नहीं होगी। This is an ideal Carnot engine which has got the maximum efficiency, which itself is not one. वो भी वन नहीं है, लेकिन कार्नोट इंजन की जो भी एफिशिएंसी है T1 और T2 दो टेम्परेचर के बीच में, ये एफिशिएंसी हमारा बनाया हुआ कोई भी इंजन अचीव नहीं कर सकता, क्योंकि और भी बहुत सारे एक्सटर्नल फैक्टर्स होते हैं। जैसे हमने फ्रिक्शन के बारे में नहीं सोचा, हीट लॉसेस के बारे में नहीं सोचा, और कैलकुलेशन की दूसरी प्रोसेसेस के बारे में नहीं सोचा है, जहां पर एफिशिएंसी इससे कम हो जाएगी। इसलिए एक थ्योरम, बहुत फेमस थ्योरम बोला जाता है, कार्नोट्स थ्योरम। कार्नोट थ्योरम ये बताता है कि किसी भी इंजन की एफिशिएंसी दो टेम्परेचर के बीच, T1 और T2 के बीच, इस एफिशिएंसी से कम होगी। It can never reach up to this level. That is Carnot's theorem. Very simple. तो इसको नोट कर लीजिए, Carnot's theorem. So for any heat engine working between two given temperatures, the efficiency cannot be equal to Carnot engine, it will always be less than it. So this is Carnot's theorem and efficiency of Carnot's engine. So from here also we can find out, higher is the temperature of reservoir, more is the efficiency. Lower is the temperature of sink, atmosphere, more is the efficiency. And this replies कि पेट्रोल इंजन और डीजल इंजन में कौन ज्यादा एफिशिएंट है? T1 फॉर डीजल इंजन इज मोर, सो इट्स एफिशिएंसी इज मोर। सर्दियों में और गर्मियों में एफिशिएंसी किसकी ज्यादा होती है? इंजन की एफिशिएंसी कब ज्यादा होती है? सो आंसर है विंटर्स में, क्योंकि विंटर्स में T2 कम होता है और पेट्रोल और डीजल के जलने का टेम्परेचर तो सेम रहेगा, इग्निशन टेम्परेचर सेम रहेगा, पर T2 छोटा होता है, सो दिस विल बी लार्जर, efficiency will be more. So these are few answers about Carnot cycle. So this is Carnot cycle. It's very important thing in engineering, because all our engines are working on this principle, and in our life everything which is converting heat to energy is working on this. Thank you.